Hello there ladies, gentlemen, boys and girls. My name is At Risk, and today in this video I want to discuss the creation of a pure sine wave inverter and the reasoning as to why you would adopt this particular technology when building an inverter. As it stands at present, there is no current video tutorial on how to build a pure sine wave inverter, or at least one that most people could reasonably be expected to follow. People have made, of course, tutorials on how to build square wave inverters that use, for example, the 4047 and a center tap transformer and two MOSFETs, of course, to drive a transformer to produce a square wave. However, if you saw AfroTechMod's video, driving a transformer to produce a square wave can often have some rather unintended consequences, and it also has a few critical deficiencies. For example, on one of the designs of the 4047 system, where you essentially use a 4047 multivibrator to produce a signal to drive a transformer. You know, as AfroTechMod said, it's perfectly good for, of course, running a light bulb, but doing much beyond that, there are, of course, some problems. And those problems, of course, are high voltage spikes, the fact the signal would run pretty poorly with anything that was particularly sensitive to signals, such as electronic fans, some computer power supplies, and various other gadgets. And there's also the simple issue that the square wave generated by a lot of these inverters does not fall into line with what you would get out of your wall socket, which is a sinusoidal waveform. So, in order to address that problem, which is that most of the inverters that you will find on YouTube and on various websites, and including on Google or DuckDuckGo, depending on whichever search system you prefer, most of the inverters actually, the diagrams and most of the videos are based around the square wave inverter. Now, as said before, the square wave inverter does not fall into line with the signal generated by mains power, which is a sinusoidal waveform. However, it is quite possible to produce a signal that is much closer in line with what comes out of the wall socket, using what is referred to as a pure sinusoidal wave inverter. Now, these inverters are a little bit different from the inverters you'll often see on a lot of these YouTube channels, and they also do come in a few different flavors and varieties. However, at the moment we're going to try to keep things simple. We're going to use easily accessible components, we're not going to use an excessive number of components, and we're just going to keep it simple and easy to follow. Now then, let's get on to the basics. In front of you is a power inverter, or a square wave power inverter. And we use these to drive transformers, and we also use them sometimes in Class D amplifiers. Now, this whole thing works simply by essentially changing polarity. If you have a transformer, right, let's say we'll spawn one now. They pretty much work by taking a DC. They pretty much work by taking a voltage. So you have one polarity. It's about to saturate the transformer. You flip the battery over, and it rinses and repeats the cycle. So it pushes and pulls current through the transformer in order to induce a magnetic field on the opposite side. This allows you to take one voltage, say 12 volts, and step it up to a much higher voltage, or potentially to a much lower voltage depending on the context. For those of you who already know, a H-bridge is designed to change polarities. So when we combined the H-bridge's ability to change polarities with the realities that exist with transformers, and put the two together, in the end what we can actually do is we can drive the transformer. So I'll just show you what happens when we pull this transistor here to on mode, and we pull this transistor on as well. We have positive here, negative here, so current will flow from here to here. Now when we connect the wires differently, this MOSFET high, this MOSFET high, the polarity changes. These changes in polarity are essentially what we call AC. So let's say we want to drive a transformer and we want to double the voltage. We'll do that now. Now, as you can see, nothing's happening because we don't actually have a signal connected, of course, to drive the transformer. However, this right here is just a stand-in for a few logic gates, but we'll go ahead and actually plug in the MOSFETs. And there we have it. What we have right here is essentially a step-up transformer configuration, where you have a DC supply of 12 volts, you have some filtering capacitors here to clean up the signal, a little driver circuit for the MOSFETs, and here you have the power stage. Now some of you may be wondering, what exactly are these little diodes here for? Well, these diodes are here to remove the inductive spikes, feed those inductive spikes here, so they won't damage any of these transistors. These are mandatory. They're what we refer to as flyback diodes, and they protect our transistors from the inductive spike generated by, of course, inductive devices. Now, for those of you who are observant, looking at the flags right here, this transformer is currently putting out a square wave signal. I'll just go ahead and adjust my oscilloscope and also Bandicam briefly. Just going to adjust this. I'll roughly double the maximum voltage. Now, as you can see here, what's happening is that we have a square wave signal. And as I said previously, feeding this square wave signal into certain AC appliances can have very undesired effects. For example, I believe in some electric motors it can actually cut the efficiency of the motor in half, and there are also various problems that ultimately occur with using square wave signals. However, it's very, very possible, thanks to an interesting little technique, to work around this particular problem, so that you can actually have a much, much cleaner signal that falls more into line with what you would expect from, say, the mains power, which I'll actually bring up right now. Of course, you'd expect a signal like as follows from your mains power, which is a sinusoidal waveform, where the increase and decrease in current is gradual rather than extremely abrupt, like it is with this circuit over here. Now, there is one issue here. This is an analog signal, which means that it operates between 1 and 0, off and on. Transistors don't like analog signals, because tran and zistor, think about what those words actually mean. If we take a resistor, for example, a transistor can be best described as essentially an adjustable resistor that can be controlled by an electronic pulse. So, if you have the transistor at 0 ohms, then there'll be 0 impedance generated by the transistor, thus 0 heat being generated by the transistor. If you run the transistor at a huge resistance, no current whatsoever will flow, or very little current. However, in the context of running a transistor at a moderately high resistance and a moderately low resistance, the issue does exist of course, generating heat. Now, for example, in a Class AB amplifier, like those big amplifiers you see in a lot of hi-fi shops and used by people with particularly fancy speakers, or in an op-amp, for example, the transistors operate between on and off in order to generate an amplified signal that, of course, you feed into the amplifier. That's essentially what a Class AB amplifier is. Those transistors operate in what's called their active region, like valves. And there is a bit of a problem with that. Running your transistors in that fashion, of course, generates a lot of heat because you're essentially causing the transistors to resist, which is going to cause problems. However, there's a very intelligent way you can ultimately deal with this problem in the context of building a pure sine wave inverter. since in the context of for example, a Class AB amplifier, efficiency is not particularly important, but fidelity is important. And in the context of a sine wave inverter, when it comes down to it, fidelity is important, but efficiency is often far more important. Because say, for example, you have a sine wave inverter that has a 100 amp hour battery, and your inverter is only half efficient, you've essentially cut your battery in half. You've increased weight, cost, size, and the need for heat sinks. However, if you, for example, have an efficiency of 90 to 80%, you're really only losing 20 amp hours over 50 amp hours. So, allow me to explain how we would achieve, of course, a pure sine wave without massively increasing, or I should say decreasing, the efficiency of the system. In order to accomplish our goals, we need a way to produce an analog signal without actually switching our transistors in an analog fashion, as this would create a lot of heat since the transistors would operate between on and off, and their resistance would be what creates this signal. Now, to do this we need to use what's called pulse width modulation, and it's pretty interesting stuff. I mean, it's essentially what a Class D amplifier uses, and this entire sine wave inverter is not particularly dissimilar to a Class D amplifier, although there are some key distinctions. The most important distinction being, and one of the most important, is the fact that we are using a much lower frequency than most Class D amplifiers would use. We're using, of course, diodes and whatnot to remove inductive spikes, and we are using all around a much lower frequency than what most amplifiers would be expected to receive. As you can see here, this is a pulse width modulated signal. The pulses gradually increase and decrease over time, and when that signal is filtered, you get your analog signal, as you can see here. Although it may be a dirty example, this is pretty much the bones of a sine wave inverter. Of course, in the real world you wouldn't be using function generators, you wouldn't use the operational amplifiers. You'd probably instead replace these here, this operational amplifier and these two function generators, with an Arduino because of their flexibility and their capabilities, or an equivalent microcontroller. And you would also replace this drive stage with something like a MOSFET driver. However, past that, what you have are 4 MOSFETs and 4 diodes. Now, the purpose of this whole driving scheme that I have towards the left in these 2 operational amplifiers is to produce an inverted SPWM signal that, when it is filtered, it will produce a waveform that is sufficient to drive all 4 of these transistors. And this waveform is essentially the exact same one coming from the Class D amplifier, albeit it flips polarities, and it also it essentially flips polarities. I mean, think if you have 2 amplifiers and one puts out a signal at one point in time, and the other signal puts out, the other speaker puts out a signal the other half of the time. That's essentially what the whole system is. When one side isn't working, the other is working, and vice versa, and that's essentially how this whole thing works. So essentially what you've created here is essentially a digital waveform that is a representation of an analog waveform that can be filtered into, of course, an analog waveform. And that's pretty much all there is to it. If you put an LC low pass filter here and a capacitor here, you hook it together, you can tap off this and you've got yourself your AC. However, there exists still one major problem. The voltage we're feeding into this H-bridge is 12 volts. Now, most inverters you buy off eBay solve this problem by building by essentially building a whole bunch of ferrite transformers and driving those transformers using another H-bridge, and of course running that H-bridge at high frequencies, and then rectifying the output of those transformers, which is roughly about 300 something volts DC, and then essentially feeding the H-bridge with that voltage and then filtering it using, of course, the capacitor and the inductor. That's how it's done, by most inverters you'll find on eBay. In fact, there's a video by a guy named Gulnar which I'm using, fair use. So I'm giving a shout out to his channel, even though his channel's bigger than mine. Which actually shows the insides of one of these inverters. Of course, you can see you have your wall sockets here, and at the back you have your inputs. So you can see here we have the ferrite transformers, the yellow things, and we have a set of transistors along the side that ultimately drive these transformers using a high frequency pulse that is then rectified somewhere along the line and then essentially switched into AC using the H bridge that we've discussed just previously in the video. And you can clearly see that right here you have your AC switching stage, where you have to the far right a bunch of transistors, which are the H bridge, and these big metal coils with red wire on them are of course the inductors, and the two little red beads to the left are actually the filter capacitors that in the end produce the signal. And over there you have, of course, the drive module and the microcontroller, as well as various other chips that drive the transistors. Now, of course, there are a few ways you could have... you could in theory use the actual boost converters that I showed in an earlier video on this channel to actually, drive one of these boards and actually get the voltage that you desire. However, in real-life circumstances, the reason why ferrite transformers are used in these systems is because they offer a much greater efficiency than boost converters, as boost converters tend to suffer from inefficiencies when there is a large differential between the input voltage and the output voltage. However, due to some obvious and not so obvious reasons, one of them being both my limitations in skill of programming microcontrollers, I don't really know how to program high-frequency PWM systems at this moment, but that is something I plan to learn. And my limitations in soldering, something I'm also looking to learn. And also the issue of components and complexity is the reason why I'm not going to be in this tutorial building a ferrite-based Signwave inverter, because it's just prohibitively expensive and complex for this tutorial. It's not really going to serve anyone as it stands currently, but there is a much better way of ultimately making a Signwave inverter given the nature and the requirements of this tutorial, which is to use an iron laminate transformer. Now, iron laminate transformers are commonly used also in, for example, a lot of the tutorials on YouTube, because they're relatively inexpensive, they're simple, and they work. For those reasons, we're going to be using iron laminate transformers in this tutorial. Now, implementing a transformer into this system, like an iron laminate transformer, isn't particularly complicated. As you can see, we have, of course, the transformer. That's a 2-to-1 ratio, and we have a capacitor on the other end, which should really be about 6 microfarads, but in this application, I'm doing 100. Now, there is one little quirk with essentially AC that it might actually cause you some problems when you're building this circuit, which is that if you have a 12 volt to 240 volt transformer and you try building this circuit, the issue of RMS comes into play, which is basically that the average voltage, like, to put it simply, your 240 volt or 120 volt wall socket is actually probably a couple volts peak to peak higher, a significant number of volts peak to peak higher than the actual voltage stated on the actual socket's plate. And the reason why is because only at around the average of that peak to peak voltage do you ultimately get the same heating effect as DC. So 240 volts AC is actually, the actual voltage is quite a bit higher. The peak-to-peak voltage is significantly higher because of the simple fact that you're only really going to get the same power, AC-wise, if you put it across, say, a resistor, at the average voltage being RMS. So you do need to wind your transformer to compensate for that, because I believe one DC volts will ultimately is the equivalent to about something in the neighborhood of, I do think, about 0.7, AC volts. So that's sort of a problem that you need to be aware of. And if you're actually winding your own transformer, like I recommend, since these inverters can be pretty beefy, you don't really need to worry about that problem too much. But you can compensate for it by increasing your input voltages, or ultimately by hooking two transformers together and adjusting amplification on your microcontroller. But yeah, that's essentially how you, of course, implement the transformer onto the bridge, and it's pretty much, that's really all there is to that particular part of the process. Now, I think that's about enough theory for this video, since it's gone on for long enough. In the next video, we'll be covering how to actually build a sine wave inverter using off-the-shelf parts, and how it can be done in a fashion that is easy to understand but simultaneously not extremely expensive. Other than that, ladies, gentlemen, boys and girls, thank you for watching my video, and I'll proceed on to making the next video, which will be the actual building and operation of the inverter. Although it is pre-built, I'll go over the parts and how the whole thing works in a built form. Other than that, like, comment, subscribe. See you later. And also, as well as a disclaimer, I'm neither a professional when it comes to the creation of video content, or when it comes to electrical engineering, which is the practice associated with what I'm doing here today in this tutorial. So take that as you will. If there's anything that you find to be confusing or in any way puzzling, do comment in the comment section below, but also as well consider watching a few videos. Channels like Afrotech Mods, for example, was mentioned in the beginning of this video, and he makes a lot of really good videos about the subject matter discussed in this theory video, and he really does put it all together. I mean, he did actually make a sine wave, he essentially laid down all of the foundations and gives you all of the knowledge you need to actually build a sine wave inverter, which is rather funny, as he said he really wouldn't build one. But that's all I can really say. Thank you, ladies, gentlemen, boys and girls. That's all.